Japan. This is the Akashi-Kaiko Bridge. With a main span of almost 2 kilometres, it's the longest suspension bridge in the world.
It's like you get a whole mile of the M25, complete with a traffic jam of trucks. You pick it up 100 feet in the air, the roadway as well, and you hold it from cliff to cliff. They're just huge feats of engineering.
Uniting people across the widest rivers and the deepest ravines. In the world of bridges, the suspension is king.
I just felt the bridge move a tiny bit then.
Right.
That's interesting.
Yeah, it's moved for you.
For 200 years, bridge builders have been trying to perfect this complex structure. They battled to overcome the elements and learnt some painful lessons, often the hard way.
You know, it's a horrible, horrible thing. It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there.
To design longer and longer suspension bridges in ever more difficult locations, this is the challenge designers face as they strive to build the ultimate. The suspension bridge is the only structure known to man that can span more than a mile. Defying gravity, it makes light of difficult crossings. From the deck and the towers, the magic of this bridge is how the load is distributed up to the cables and into the anchorage. This bridge must deal with many forces: its own weight, the weather, and the weight of traffic. Every year, 40 million vehicles cross the Golden Gate Suspension Bridge in San Francisco. The Menai Strait Suspension Bridge in North Wales is one of the oldest in the world. Most of its contemporaries collapsed due to bad design and a lack of understanding of how this bridge really works. Chris Wise designed the London Millenium Bridge and is a professor of civil engineering design. Like all engineers, he's constantly second-guessing the possible threats to the suspension bridge.
When we work through a bridge design, we take all the obvious things, every single natural phenomenon that we can imagine, so gravity, wind, hurricanes, and then we also have to think about what happens if a terrorist attacks a bridge, because a real major bridge like this is a fantastic target for terrorists. You imagine somebody going for the Golden Gate Bridge or the Sydney Harbour Bridge. So we have to consider when we're designing these things, what would happen if somebody cut one of the cables, for example. And the Millennium Bridge is designed so that a certain number of cables, and I can't tell you how many, can be taken out by a terrorist attack and the bridge will still survive.
With nothing supporting it from underneath, the length of a suspension bridge is calculated by the span between the two towers. The towers in a suspension bridge are like the poles in a washing line. The main cable hangs between them.
Well, the towers they're probably the most important thing. If the towers fail, the whole bridge falls down.
But just how the towers work is a surprise.
They have similar properties to a tree. If you imagine a tree in a strong wind, it doesn't try and stand there and resist the wind by just going like that. It actually allows it gives, and in giving, it allows the wind to dissipate its energy.
It took many years for engineers to learn the basic principles. Without a few key pioneers, we wouldn't have the suspension bridge we see today. The Clifton Suspension Bridge is a masterpiece of engineering, designed by 23-year-old Isambard Kingdom Brunel in 1829. So perfect was his design that it remains structurally unchanged to this day. Sadly, Brunel died 5 years before it was finished. The masonry towers are 26 metres high, but it soon became clear that masonry had limitations. Longer bridges needed taller towers. Masonry towers could never be tall enough. And this wasn't the only problem with it. Masonry is a brittle material. If shaken, it collapses like a deck of cards. This is the aftermath of the San Francisco earthquake of 1906. 25,000 buildings were destroyed. Nowhere were the limitations of masonry more obvious. Then came steel, and with it the chance to build higher towers and so longer bridges, like the Golden Gate. And steel had another advantage in earthquake zones like San Francisco. it was ductile.
Ductile means that it doesn't snap easy. It's the opposite of being brittle. So with ductile, there's two reasons you want it to be ductile. One is because it gives you a warning that it's about to go, that when it first starts to really bend, you can see that something's happening. And the other one is, in a dynamic case, it absorbs energy because you can go backwards and forwards. Whereas with brittle materials, it just goes bang and everything falls to the ground. You have no warning, there's no energy absorption, everything just breaks all at once.
When the Golden Gate Bridge opened in 1937, it became the longest bridge in the world. With towers of almost 230 metres, almost 10 times taller than the Clifton Suspension Bridge, the Golden Gate became a world icon. For 50 years, steel ruled, but it came at a high price. So in the 1970s, designers came up with a solution to unite the flexibility of steel with the convenience of concrete. The way forward was steel-reinforced concrete. Fulfilling a personal ambition, Chris Wise goes to see the inner workings of the first bridge in the world to be built with concrete towers. The Humber Bridge in East Yorkshire.
No, it's surprisingly well behaved. I mean, I was expecting to see it, to almost see it moving. Because when you look at it from ground level,
yeah,
it looks so slender. You know, you see this fantastic thing just going across the water, and it's you know, you almost expect it to be moving around. It'd be a bit more lively.
Opened in 1981, the Humber Bridge is today the fourth longest in the world.
How fast is the wind actually going?
About 10 metres per second.
10 metres, it's about 25 miles an hour, roughly.
Going up to...
Actually, I just felt the bridge, I felt it move a tiny bit then.
Right.
That's interesting.
The Earth's moved for you.
Yeah.
With reinforced concrete towers, suspension bridges can now be built at a speed that would have astonished the early pioneers. But the real ingenuity of the suspension bridge is the suspension system, made up of the main cable and hangers. Everything depends on the cable, but it's also the bridge's Achilles heel. When Brunel built the Clifton Suspension Bridge, he used 4,200 second-hand chains that had been on the Hungerford Bridge in London.
Historically, they used to use chains for suspension bridges, and they made the cables out of wrought iron chains made out of loads and loads of individual pieces, and it was very complicated. It took ages.
Heavy chains meant that much of the bridge's strength is taken up in carrying its own weight, so span and traffic is limited. Then, towards the end of the 1800s, one man working in America was about to change that. This is the Cincinnati Roebling Bridge, named after the man who designed it, John Roebling. A tortured genius, he was obsessed with pioneering a new design in bridges. The Cincinnati Bridge was just a dry run for a bridge that would make Roebling an international name. In 1883, the Brooklyn Bridge in New York was about to become the world champion. On its completion, its towers would stand at 84.3 metres, the tallest structures in Manhattan at that time.
What amazes me the most about the Brooklyn Bridge is its complexity and the time period that it was built in. You have to remember, this bridge was started in 1869, just a couple years after the Civil War. There was no electricity, there was no machinery, no gas combustion engines. This bridge was built just with the use of steam engines and was literally built by hand.
But Roebling's true genius was in how he made the main cable. He didn't use wrought iron chains. Instead, he used the most modern new material, steel. And to make the bridge lighter, he spun the steel back and forth across the river.
Hey, the main cable is the lifeline of the bridge, and this cable is made up of thousands of bridge wires which are about the diameter of a pencil. And there's literally thousands of these wires within the main cable itself.
This move to spun cables in New York in the 1860s changed the face of the suspension bridge forever. 100 years later, when Doug Strachan worked on the construction of the Humber Bridge, cable spinning had become an art.
We take a spinning wheel across the river, and when the spinning wheel gets to the anchorage, the loop is taken over and the wheel comes back empty. They then take another loop and the wheel starts off again at the anchorage, taking the second loop of wire across the bridge, and in that way you build up the cable of the bridge.
The cable is then anchored with a huge amount of concrete into the ground.
How many strands of wire are there in this fantastic contraption?
Well, the whole shebang's 15,000 wires, but the reality is there's only 37 wires, and they all, each of them crosses the river 400 times.
They look like they last forever, these things.
Well, they're supposed to have a life of 120 years. This is, if anything, the Achilles heel of a suspension bridge. Very, very difficult to replace. And somebody once said that trying to replace the cables on a suspension bridge is like going to the dentist, and he says, well, your teeth are all right, but your gums will have to come out.
The huge leaps forward in the technology of the suspension system have enabled designers to increase span, connecting more and more people over greater distances. But once the cables were finally perfected, it was clear to engineers around the world they had a lot of work to do on the deck. By the mid-20th century, the suspension bridge had come into its own. But in November 1940, something happened that would change these bridges forever. The Tacoma Narrows Bridge in Washington State opened in July 1940 and hit instant fame. Christened Galloping Gertie, this newly opened bridge began to oscillate uncontrollably.
It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there. You know, it's a horrible, horrible thing.
On the 7th of November 1940, Galloping Gertie collapsed. For designers, nothing would ever be the same again. The collapse of the Tacoma Narrows was a wake-up call for suspension bridge designers. In pursuit of slenderness, they'd underestimated the power of wind. The mystery lay in the fact that Tacoma was designed to withstand 120-mile-an-hour winds. Yet the wind speed on the 7th of November 1940 was only 40 miles per hour. The key to unlock this mystery would be found in a phenomenon called natural frequency.
Natural frequency is it would be something that's very familiar to anybody who likes music. It's the note that something makes. And if you pluck a guitar string or a violin string, you hear a note which has a particular frequency. And bridges are no different.
We've got three structures here. They've each got a different natural frequency. The natural frequency is the frequency it wants to vibrate at if you just give it a twang. And so we've got a really slow natural frequency here, got a really fast one, and we've got one in the middle.
In this test, the Tacoma Narrows natural frequency is most similar to the slow one. When winds hit a bridge, they create mini whirlwinds, called vortices. The problems start when these vortices have the same natural frequency as the bridge. This is called resonance.
If I now start to shake this support for these three bridges, if I do it really slowly, just give it a little motion, at the natural frequency of my big slow one, you can see that the big slow one really starts to respond, and we get massive amplification. And the other two are hardly doing anything. If I do it at intermediate sort of speed, the middle one goes wild and the other two stop. And if I go really fast, just the little one goes wild and the other two stop.
On that morning, with vortices created at the natural frequency of Galloping Gertie, it was only a matter of time before resonance caused the bridge's collapse. Tacoma terrified bridge engineers. Suddenly, wind was the enemy. They went back to the drawing board and discovered that the way to combat resonance was to bolt extra beams underneath the deck, called a stiffening truss. At vast expense, bridges around the world, including the Golden Gate, were retrofitted. It seemed the stiffening truss was the only way forward. That was until the late 1950s, when a young British designer came up with a new idea. And after countless awards, more than 40 years later, Bill Brown still plays down his role.
I think I was probably at the right place at the right time, in fact.
The magic of Bill's idea was to work with the wind rather than against it.
I didn't know that it would work aerodynamically. I knew it would work structurally, but not whether the aerodynamics would work.
Bill came up with the idea of reshaping the deck of the suspension bridge to make it aerodynamic. The wind is deflected around it, and the deck flies in the wind. Bill had just finished the 4th road bridge and had won the commission to build a crossing over the River Severn. This would be the first bridge in the world to have this new deck, but first he had to test it. 40 years later, Bill demonstrates what his wind tunnel tests showed. First up, he tests the Tacoma deck.
You can see the Tacoma Narrows section is twisting quite violently.
At just 40 miles per hour, the Tacoma deck cannot withstand the wind.
I think that's enough, otherwise we'll damage the models. So we take this and we'll now put in the model of the Severn Bridge, which is a longer span of different cross-section, and we'll run it at a much higher wind speed.
The effects of the wind on the aerodynamic deck are plain to see.
We now have mounted the Severn cross-section, and we're running this now at 150 miles an hour. And as you can see, it is absolutely stable. This is because we have an aerodynamic section, the wind is flowing above and below it, streamlined, and the forces are low.
The Severn Suspension Bridge was opened in 1966 and would lead the way in modern bridges.
The magic is that it is streamlined and therefore the wind forces are low and there are very few vortices. So generally speaking, we don't need to add structural resistance to overcome the wind forces.
After the success of the Severn, bridges around the world were built with aerodynamic decks, starting with the Humber.
This is Bill Brown's aerodynamic deck, is it?
Absolutely right. It's quite flat over the top and then quite low down here, so you get the right aerodynamic effect. So
the wind goes over the top.
Yeah, the wind route over the top is shorter than the route underneath, so it's an upside-down aircraft wing. It's got negative lift.
Resisting wind and earthquakes is a challenge, but there are other forces of nature out to get the suspension bridge. Over the years, engineers thought they understood the effect of people walking on a bridge, but they didn't.
Those you two! Break step!
Everybody knows about the Roman army having to break step when they go across bridges, and the reason for that is because they march very regularly. You have lots of people all putting their feet down at the same time, and if you get a bridge which happens to have a frequency which is close to that, the Romans must have found out 2,000 years ago that if they didn't break step, they would actually knock the bridges down.
2,000 years after Roman soldiers marched on London, this issue of footsteps would be a problem for Chris and the team at the grand opening of the Millenium Bridge over the Thames. Opening day, June 2000, and the bridge did what no one expected. It started swaying from side to side. The first Mike Wilford knew about it was when his telephone rang.
I had a phone call from one of my colleagues who was on the bridge asking me whether I'd come down and take a look at it because it was vibrating. And I said, goodness, not bouncing up and down, is it? It shouldn't do that. He said, no, it's going from side to side. And that seemed very strange to me. So I got in the car and came down to take a look at it.
This swaying bridge caught the headlines and became talk of the town.
Obviously, it's the sort of thing you dread. You know, I hate the fact that the bridge didn't work perfectly.
We were a bit embarrassed that the bridge wobbled in a way that wasn't predicted or wasn't expected.
Designers needed to act, and to act quickly. From looking at the bridge, engineers discovered that the swaying was caused by people's footsteps.
There were enough of them that they, strangely to us, all decided to walk at exactly the same speed, and we couldn't understand what the hell was going on.
What people were doing was synchronizing their footfall, not up and down like marching soldiers, but from side to side.
What we found was that when the deck you're walking on moves a little bit side to side, you tend to synchronize your footsteps with that motion and also place your feet further apart to improve your balance. This increases the lateral forces on the system, so the sway gets bigger and bigger.
Just like a child's swing, the bridge created its own positive feedback, and with every sway, it gained momentum. This movement was christened synchronous lateral excitation. Engineers had known about it in theory, but this was the first time they began to really understand it.
It did put the spotlight on lateral excitation, which most suspension bridge designers had never worried about before for people walking. They'd always concentrated just on the vertical. Now we do have to think about the lateral a lot more.
The problem that took time to understand was quick to solve.
It was solved by putting dampers on it. You just put these big, like bicycle pumps full of honey, and they just drain the energy out of it. If the structure moves, these dissipate energy. It's very simple to fix.
This new discovery caused a stir around the world.
Every bridge around the world was checked for this phenomenon of synchronous lateral excitation to make sure that it wouldn't happen on their bridge. And many of them, it turned out, had actually been moving very quietly without anybody really mentioning it, because everyone was too embarrassed about it. But a lot of bridges have been retrofitted with dampers as a result of the problems that the Millenium Bridge had.
With every new bridge built comes a greater understanding of the dynamics of the suspension bridge. Getting a grasp on resonance and aerodynamics means decks are now safer and longer. For the past 200 years, the suspension bridge has evolved to span greater and greater distances. But despite all these advancements, engineers still think it can be improved.
Most people who design bridges want to stay just on the side of danger. You know, they try and be a little bit conservative. And as a result of that, you see an awful lot of bridges that look almost exactly the same all over the world, and many of them are horrible. But sooner or later, somebody has to be adventurous, and bridge designers who do that need to be applauded, because if they didn't have that degree of adventure in them, the technology would never move forward, and we would never have been able to get from one side of the Thames to the other, ever.
40 years after his revolutionary Severn Bridge, Bill Brown is still pushing new frontiers. Today he's designing a bridge that will be more than a kilometre longer than any bridge yet standing. And there's a new generation of bridge around the corner. Engineers will soon be harnessing computers to their suspension bridges.
I think that the future of suspension bridges will be actively controlled bridges. And when a hurricane hits them, something will happen, a servo will kick in, and it'll pull the bridge away from the hurricane to make it stand up.
Bridges able to make decisions when faced with unexpected forces means the suspension bridge will unite even more people as they span ever greater distances.